All right, chapter 11, let the party begin. So, chapter 11 is all about looking at a molecule and understanding what a molecule looks like in 3 dimensions and getting some characteristics about it. The first part of chapter 11 is taking the Lewis structures of molecules that we've drawn previously, those 2-dimensional representations, x and y axis 2 dimensions, and trying to visualize them and speculate what they would look like in 3 dimensions. Because as we know, we live in a 3-dimensional space, x, y, and z plane. Like my hand goes in one direction, not one direction, but towards something. And so molecules exist in 3 dimensions, not simply on an x and y plane. So we try to use this thing called Vesper Theory to come up with the shapes of a molecule. So Lewis structures are 2-dimensional models. However, we know that molecules exist in 3 dimensions, and so we need to know the 3-dimensional shape of a molecule in order to determine some physical and chemical properties of those molecules. So as an example, here we've got the Lewis structure of 1-butanol, and here's the Lewis structure of 2-butanol. Now, we've got some properties of them, and unfortunately my face is blocking one of them that has a stark difference, but I'll go ahead and draw a line to it. 1-butanol with this shape in 2 dimensions has approximately this shape in 3 dimensions. This would be a hydrogen right here, and this is another hydrogen. And the second hydrogen that I listed is behind the first hydrogen. So it exists in 3 dimensions. Now, some of the properties about them. They're both less dense than water with a density of 0.81 grams per milliliter, but the melting points, they range from negative 89.8 degrees Celsius to negative 115 degrees Celsius. The boiling points are different, being at 117.7 to 99.5 degrees. The solubility of these in water is different, and their flash points are different. And this has to do with what they exist like in 3 dimensions. So, valence shell electron pair repulsion model, or Vesper model, predicts the shape of a molecule based on the number of electron domains surrounding the central atom. Okay, before we get into that, I want to show what constitutes an electron domain. So I'm going to draw water. We've got oxygen, hydrogen, and then water also has 2 lone pairs of electrons. I'm going to switch colors, and I'm going to draw a circle around the electrons of a given electron domain. Here's one, here's another, here's another, here's another. Okay, so a single bond, a double bond, or a triple bond constitutes an electron domain. A lone pair of electrons also constitutes an electron domain. So something like water has a total of 4 electron domains. So I don't want you to get distracted and think like, oh, is it a single bond or a double bond? Does it matter? No, it doesn't. It really does not matter. So now let's go back to this. Each electron domain is a charge cloud made up of either a shared or lone pairs of electrons. So we saw that. Here's a shared pair, and here's a lone pair, and a shared pair. I don't know why I scribbled there rather than just writing SP. At any rate, the most stable arrangement is one with the least repulsion between electron domains, with the domains where the domains are as far apart as possible while still connected to the central atom. Now, that's something that's kind of difficult to wrap your mind around, but this lone pair of electrons and this lone pair of electrons, what they're going to do is they're going to be repelling one another, and they're going to be repelling the shared pair of electrons. So there's all these repulsive forces because these electrons, well, they're all negative, and so they're going to be pushing away from one another. So we want to basically come up with a structure where the repulsion is as low as possible. Okay, so this most stable arrangement is the electron geometry or the domain geometry. The molecular geometry is the shape occupied by the atoms in a molecule. the electron geometry of a molecule determines its molecular geometry. So what we first want to wrap our minds around is, what is the electron geometry? Because that tells us where the electrons are. Then once we know where the electrons are and what space that they need to occupy, we can use that to consider the molecular geometry. Now this table right here is a very important table. And we're going to go over this over the course of the next, I believe, 3 slides. And what I'd like you to focus on first and foremost is the first column, electron domains, 2, 3, and 4. We just talked about an electron domain either being a shared pair of electrons or a lone pair of electrons. Now, in this first row, we've got 2 electron domains, and the way that that can exist is it can be 2 bonded groups of electrons without lone pairs. Okay. After that, we get the electron geometry and the molecular geometry, as well as the bond angles. And we're given an example of that. Carbon dioxide, for instance, is an example of a linear molecule that has a total of 2 electron domains. Carbon dioxide, if you want to draw the Lewis structure, looks a little bit like this. You got lone pairs on oxygen, lone pairs on oxygen. There we go. That is a linear molecule. It's 180 degrees between here and here. It's 180 degrees between here and here. Okay. Now, when we go on to our next electron domains, where we have 3 electron domains, things get a little bit more complicated. Because what we can have, what combinations can come from that are, we could have 3 bonded groups, or we could have 2 bonded groups and 1 lone pair of electrons. Now, the rest of this table shows us everything about the electron geometry and molecular geometry, as well as gives us a couple of examples. Now, for our 4 electron domains, that can be 4 bonded groups, or 3 bonded groups and 1 lone pair, or 2 bonded groups and 2 lone pairs. So what I'd like you to recognize about this is all of the different kind of combinations that can stem off based on the electron domains. Then I'd like you to consider, well, what's my electron geometry? The first, what I'd like to focus on is electron geometry. Now, your electron domain number is going to tell you about the electron geometry. It's going to tell you explicitly about the electron geometry. If there are 3 domains, your electron geometry is always trigonal planar. If you have 4 domains, it's always tetrahedral. That's your electron geometry. So the positioning of our electron domains. Now, where there's variation, on the other hand, though, is in your molecular geometry. If there are 3 bonded groups, then you have a trigonal planar molecule. So your electron geometry and your molecular geometry are identical. If, however, of those 3 domains, one of them is a lone pair of electrons, that means the other 2 are shared pairs of electrons, then you have a bent molecule. Okay? So your molecular geometry, if you have 0 lone pairs, then your electron and molecular geometry are identical. But as soon as you start including lone pairs of electrons, things get a little bit different. And a fair question to ask there is, why? Well, the reason why is because of the fact that with these lone pairs of electrons occupy more space than a bonded pair of electrons. And so they have more repulsive force than a bonded pair of electrons. Okay, so familiarizing yourself with this table is an important thing. Looking at these examples and drawing these molecules, so I'm going to go ahead and draw NH3 up top here. NH3 looks something like this, H. We've got a lone pair of electrons. So this lone pair of electrons basically is repelling everything down. H2O, which I drew a little bit ago, now I'm going to draw it again over here. There we go. So these are, I would say that the most important things about this are that you're able to discern or determine what your what the impact of a lone pair of electrons is going to have. On the surface, it's going to change or it's going to make your molecular geometry different from your electron geometry. And that could be, and basically I want you to think about why. And the biggest reason for that is that lone pair of electrons is going to be repelling everything else. All right, so next, if you have 5 electron domains, you have a couple of different options. One, you could have 5 bonded groups. Again, your electron geometry and molecular geometry is identical. You could have 4 bonded groups and 1 lone pair. These are different. Electron and molecular geometry are different. If you have 3 bonded groups and 2 lone pairs of electrons, again, molecular and electron geometry are different. If you have 2 bonded groups and 3 lone pairs of electrons, again, finally, your electron and molecular geometry are different. Now, this shows a couple of different representations of what our molecules are going to look like. And maybe one of the most important parts of this is the fact that if you have 5 electron domains, you are drawing a molecule that is an exception to the octet rule. So SF4, for instance, sulfur tetrafluoride. Well, if you wanted to draw that structure, you got to add up and figure out how many electrons does sulfur have. And you would see that sulfur has a grand total of 6 electrons, 6 valence electrons. Each one of these fluorines has 7 valence electrons. 6 plus 4 times 7 equals 34. So we've got 34 electrons. And so you're going to have how many lone pairs of electrons? Just 1. So here's a modified but good version of what SF4 is going to look like. All right. Finally, if you have 6 electron domains, well, this is what your molecule is going to appear as. We've got, there we go, I lost my cursor. 6 electron domains, you can have 6 bonded groups and 0 lone pairs, 5 bonded groups, 1 lone pair, or 4 bonded groups and 2 lone pairs. And here's what our molecules, here's some examples. SF6CL5 or CLF5XE xenon tetrafluoride. This is worth noting because over the course of the semester, we've talked about how noble gases don't like to be involved in bonds, and that's true. But can it, or can they? Absolutely. So this is one example of those. Our electron geometry and our molecular geometry remains the same so long as we don't have lone pairs, but as soon as we add a lone pair, well, then our molecular geometry is a little bit different. All right, well, that concludes section 11.1. I hope that was helpful. Hope you guys have a good one, and I'll see you in 11.2.